Welcome back to The Explainer. Today we are putting together what I think is an absolutely critical open source intelligence briefing. If you're a university-level engineering student, a systems analyst, or honestly just someone who is fascinated by the mechanics of orbital physics, this one is right up your alley. We're going to completely deconstruct the photon-level physics, the strategic doctrine, and the really severe economic fallout of Russia's Kalina ground-based anti-satellite laser. So here is our roadmap for today. We'll start with the OSINT briefing on the facility itself and the physics behind how it actually works. Then we're going to trace the evolution of this directed energy tech, see how it fits into broader military doctrine alongside China's Bohu site, and finally, look at why this is causing a massive systemic panic for commercial satellite insurance. Let's dive right in. Starting with Section 1, the Kalina OSINT briefing. Let's set the macro scene first. Okay, we have to begin with this chillingly precise objective, the functional suppression of spacecraft. Now, what's incredible about this is that it isn't just some wild guess from a Western intelligence analyst. This is a direct, verbatim quote extracted from a 2014 Russian Ministry of Defense bank guarantee document. It was filed by the contractor NPK SPP. So this is a declared, documented, and fully funded mission. Let's look at the physical footprint for a second. Kalina sits at the Krona complex over in the Caucasus Mountains. Now, for the engineering students watching, you'll immediately spot why they chose Chapel Mountain. Sitting at over 2,000 meters, it's way above the denser parts of the troposphere, which gives it that optimal atmospheric stability that astronomers call seeing. And tucked right inside Building 00877S, under a 7-meter dome, is the primary optic, a massive 1-meter f1010 mirror. Moving to Section 2. Let's zoom in from that macro facility down to the micro, photon-level physics that actually cause the damage. Geeking out just a little bit here, we are dealing with a solid-state ND YAG laser. It emits at 1.0645 microns, so we're talking near-infrared, and it fires these incredibly brief pulses, just 10 nanoseconds long, but with a peak power density of 0.1 gigawatts per square centimeter. To put that into perspective, this is definitely not a harmless laser rangefinder. It is explicitly engineered to deposit a catastrophic amount of thermal energy onto a sensor in the literal blink of an eye, way before the target satellite even has a chance to rotate away to protect itself. So let's walk through the actual engagement cycle. First, the radar acquires the target, and then LiDAR characterizes its exact orbit. But Step 3 is where the true engineering marvel lies. It's the F1040 deformable mirror. This adaptive optics system actually uses the target satellite itself as a guide star. It pre-compensates the laser beam for atmospheric turbulence before it even fires. Once it corrects for that distortion, it blasts that massive beam straight through the atmosphere with almost zero spreading. Because of that precision, we're looking at 3 distinct damage thresholds. Threshold 1 is just dazzling, temporary, reversible sensor blindness. Threshold 2 introduces permanent dead pixels. And while mobile laser systems generally max out at those first 2, Kalina's immense power and fixed adaptive optics are designed for threshold 3. We're talking catastrophic, permanent ablation of the satellite's focal plane array. It's essentially frying the digital retina of the camera entirely. All right, Section 3, the evolution of directed energy. Because a ground-based system this complex absolutely does not just appear overnight. If we trace the engineering arc here, we're looking at a 60-year R&D pipeline. The Soviets were testing the Terra 3 laser way back in 1971. By 1982, they were fielding the Stillet laser tank prototypes. Fast forward to 2009, and they're testing the Sokol Echelon airborne laser directly against a satellite. All of that surviving expertise, the optical designers, the adaptive optics specialists, that all funneled directly into the modern Kalina dome construction in 2022. It really highlights the relentless evolution of their directed energy programs. Which brings us to Section 4. Let's zoom back out and contextualize how this engineering fits into their broader military strategy. The governing framework here is a doctrine called Bezkontaktnaya voyna, or non-contact warfare. The whole idea is to target an adversary's critical support systems, especially their reliance on space-based reconnaissance, across all domains, but without necessarily causing physical kinetic destruction, so no debris fielding orbit. Kalina is really just one piece of a multi-domain layer cake designed to systematically dismantle that reliance from the ground up. Looking neutrally at the data, you can clearly see this integrated architecture taking shape. You've got ground lasers like Kalina targeting low Earth orbit, terrestrial electronic warfare jammers like Tobel blinding GPS, and co-orbital inspectors way out in the geostationary belt. Crucially, during an international crisis, this architecture allows a state to instantly create massive blind spots for adversary reconnaissance. It completely denies situational awareness right when it's needed most. And watch how this capability builds geometrically across the globe. If you draw a direct operational line between Kalina in the Caucasus and China's Bohu facility in the Xinjiang desert, a clear pattern emerges. Kalina relies on complex adaptive optics in a high-altitude environment, whereas Bohu uses a much larger 12-meter dome, which suggests they rely more on sheer chemical laser output power to just brute force burn through the atmosphere. But together, these systems demonstrate how nations are projecting power to aggressively contest the airspace above the entire Eurasian landmass. Moving to Section 5. Let's shift our focus to the actual targets up in orbit and the massive asymmetry of this threat profile. The true scope of the vulnerability here is pretty staggering. Out of roughly 2,800 electro-optical satellites currently in orbit, fewer than 50 are dedicated military spy satellites. The vast majority, around 2,750 of them, are civilian and commercial platforms. These are the exact satellites we rely on for open-source intelligence, European agriculture, global climate science, you name it. And right now, they are all sitting directly in the crosshairs. And remember the physics we discussed a minute ago? Well, the laser really doesn't care whose flag is painted on the side of the satellite. In a super cruel twist of physics, the laser's irradiance is actually multiplied by the square of the satellite's own optical magnification. It is quite literally like using a magnifying glass to burn a leaf, except the satellite is holding the magnifying glass itself. Its very own focusing optics become the instrument of its destruction, absolutely guaranteeing a blown-out sensor. Finally, Section 6, the orbital insurance crisis. Let's explore how that physical damage threshold we just talked about triggers a devastating economic chain reaction. Since 2022, the commercial Earth observation insurance market, specifically over at Lloyd's of London, has seen a staggering 300% spike in hostile interference claims. Let's just map out the cause and effect of that number. The fundamental actuarial assumption of a safe, permissive orbit, it's been permanently broken. If commercial space insurance premiums continue to spike, or worse, if we start seeing market-wide coverage refusals over Eurasia, data sovereignty will essentially be enforced by lasers. Think about it. If you cannot insure these commercial satellites, the entire global Earth observation business model faces total collapse. Which brings us to one final, highly provocative question. How does global transparency survive when the airspace above the Eurasian landmass becomes a completely uninsurable optical kill zone? It is a profoundly chilling future for orbital transparency and a massive challenge for the engineers and analysts who are going to have to navigate it. Thank you so much for joining me for this explainer. Keep analyzing, keep asking those hard questions, and I'll see you in the next one.